Hello, my name is Noah Bailey and welcome back to my ECE5000 electrical engineering design project. This is part 5, the finished product. My project is a 120 volt AC load measurement device. It can measure and display the voltage, current, power, and energy of any AC load. My design project is a 120 volt AC load measurement device. It can measure and display the voltage, current, power, and energy of an AC load, and it is based entirely on the Arduino Uno R3. So let's go ahead and jump into what has changed since the last submission. So the first notable change is that the housing that contains all of the components and the overall design is now labeled. This includes a voltage label with the positive and negative terminals for the voltage on one side, as well as a current label with the in and the out, or positive and negative, for the current sensor on the other side. This is a safety feature so that somebody doesn't accidentally flip them and end up hurting themselves or hurting the design or the boards or the sensors. And so this is just an overall general safety feature. I will show you what that looks like here. Next, I made some minor adjustments to the code. So in the original code, the way that the voltage was displayed was that numerous sample measurements were taken, and then these samples were averaged and displayed every 800 milliseconds. But in terms of the current was just measured at the moment of display. So that meant that the current value tended to jump around a lot more than the voltage value. So I went ahead and changed the code so that the current is now measured the same way as the voltage, as in numerous sample currents are taken and then these are averaged for the duration of the 800 milliseconds, then displayed to the screen, which gives a much more stable current for the display. Also, this was discussed last time, but all of the components are attached to the Arduino shield, and for the most part they are soldered on so that these connections are secure and safe. Everything is insulated with either electrical tape or heat shrink, and it's just more of a permanent design now inside of the housing. Since last time, it hasn't really changed much. I've cleaned up some of the solder and some of the connections are a little bit more secure now, but other than that, it is still the same as was seen in the testing phase. Next, I'll just jump in and show how the code has changed on the computer. All right, so here we are in the Arduino IDE taking a look at the code. And as I mentioned, the only change that has really been realized in this code is the way that the current is measured and displayed. So we'll just run through the rest pretty quickly here. Firstly, I include the needed libraries right here. I set up the file, which is going to be used for the SD card. I set up the button, which involves the pin and the LED pin, and the LED state gets set to low, and we initialize a button state. I set up the LCD, which is pretty straightforward. These are just all of the ports, or the pins on the LCD, and what ports they relate to, and then initializing that. Here is where I set up for the voltage measurement, and now also the current measurement in a way. So here we can see that before, where there was just voltage sample read, now there is also a current sample read. Same with the voltage sample sum, there is now a current sample sum. I reused most of the code down here, which is the current sort of model and sensitivity and whatnot. And then down here, I just have a MISC set up for the power, energy, and total energy, which are going to be displayed. Then we have the void setup, which is run once at the beginning and then is never run again, and it just begins the LCD, which is 16 characters by 2 rows. It establishes that the button is an input, the LED is an output. These are for the safe eject of the SD card, and it reads the button state, and then we get the serial.begin so that the serial logger and plotter begin, and initialize SD is called. As I mentioned last time, the initialize SD I would frequently comment and uncomment, due to the fact that I didn't want to move the SD card back and forth numerous times when testing. So when it's commented, the code works fine without the SD, but if you were to leave it uncommented, the code will not work without the SD card being in the SD card module. Now let's jump into the main loop, where the actual only real changes, in a way, happen. So before, we only had voltage sample reads, which is some math and just some general formulas to get a sample sum of the voltage. Now we have added the same exact steps with the current. Now this looks confusing, but if we go down here where these comments are, is what the current was previously, how the current was previously calculated. So previously there was a raw voltage that is being read from the pin that the current is attached to. Then the voltage is adjusted to make that the voltage is 0 when there is no current, as there sometimes can be phantom currents. So you just have to adjust the sensitivity of that here. And then the current is calculated using the sensitivity of the model and the voltage that is being read from that analog port. So I've combined all of those into one step up here, which gives a current sample read, and then it sums all of those together. And then we can actually use the sample count of the voltage identically to the sample count of the current, because they will both be sampled the same number of times. As we will see down here, the current mean and the voltage mean are both divided by voltage sample count, as they are both the same. The count will be the same for the current and the voltage, as they are sampled at the same time every time. And then these are the values that are displayed and used to calculate the power and the energy. As I mentioned, the energy, we know that the sample is every 0.8 milliseconds, or 0.8 seconds, 800 milliseconds. And so we can simply calculate the energy using that value. So here we can see the serial prints, which are not actually used in the final design as it is not attached to a computer. But we can see here current was replaced by current mean. This is the same for the LCD. Current was replaced by current mean. And the SD card, where current was replaced by current mean. Here we can see that the sample sums were reset at the bottom and the sample count is set back to 0 so that the process repeats. And then here we can see that the button state is checked to see that if the button state goes high, eject SD function is called and the LED is written high. The eject SD function is down here, and it just closes the file so that no data is corrupt or anything along those lines, so that the SD card can be removed safely and moved over to a computer. We also see that the initialize SD, which was commented and uncommented above, is right here, and this is some basic setup that comes along with using the SD card module to make sure that the SD card is formatted properly and connected properly and good to be done. And you can see in the serial logger when you're using it that it will say initialization done if the SD card is initialized properly, and it will write a little test, as we will see when we look at the SD card text file in a bit. Now let's go ahead and take a look at some of the testing and the demos that I've done with this design since the last segment. Since last time, where I only tested on a light bulb, I have fully deconstructed my household toaster so that I could get at the inside, make my own modifications and adjustments, and measure that load. I will show you what that looks like right here. Doing this, my toaster obviously uses 120 volts and around 10 or 11 amps for a max power of 1400 watts. Now, when I tested this, I got values that were pretty close to this, and thus it was pretty accurate. The 11 amps is a little scary because that's a pretty high amperage, but where I went with the 20 amp model of the current sensor, that was no issue. And I have wires that are well within the support range of that, so that I know I'm not going to cause any damage. I also still obviously have my light bulb setup that we saw last time that is currently set up actually. I re-insulated all of the connections to that and reset it back up with the dimmer switch, or the potentiometer, which is just a dimmer switch. And we'll just do another little demo of that right now. I'll show you the light bulb going up and down. Now this light bulb is a very, very low wattage in compared to the toaster. So obviously the readings of power and current are going to be much, much smaller, but it is of the same effect, and I just happen to have it insulated and ready to go right now, so we'll just do a little demo with that one. But we will see the toaster again in the full in-depth demonstration in the next part, which I will discuss later. Alright, so here is just another little demonstration with the light bulb as I mentioned. I have all of the connections on this tested, secured, and insulated, so it's safe to test, and it's a low wattage, so it's pretty safe. Here I am just plugging in the design with the 120 volt to 9 volt power adapter, and here I am just flicking on the bulb. Here you can see it's off. I'll turn up the potentiometer. It will get as bright as it can. I'm checking the values to make sure that they line up with what is expected, and here I will grab the camera and show these values on the LCD. I'll give a little tour of the setup here. We can see the potentiometer there. The light bulb is plugged into a power bar. Here are all my wires. You can see the labels for voltage and current, positives and negatives, and we can see that it is reading 122 volts, which is around expected for the highest voltage. I'll turn down the dimmer switch, the bulb will get dimmer, and we should expect a lower voltage. We can confirm here that we do see a significantly lower voltage. As I continue to lower it, the bulb will get darker and darker as less voltage drops across it and more across the potentiometer. We can see that reflected on the LCD. Then I'll just go around to the back here where I have left it open to access the parts, and I will press the safe eject button, which is on the Arduino shield, and we will see it lights up bright blue. This means that it is safe to eject the SD card here, which I will pop out, and we'll hop over and take a look at that text file that was created. Alright, so here we can see the SD card file test. It's just a .text file. As we can see, as I mentioned, there's the testing at the beginning, and then it starts to read some values. Now this file tends to grow quite quickly as you are reading values. You can see sometimes it reads no values, sometimes it reads values. This is because the design is often turned on and off while it is being tested. But as we continue to scroll down here, we can see that the most recent readings were 2.78 volts, 0.5 amps, which gives a power of 0.14 watts and a total energy that accumulates over time, which can then be averaged to find the average kilowatt hours or whatever unit of energy you would like. But this voltage reading, current reading, and power reading were calculated or measured rather using the light bulb on the dimmer switch, and adjusting the dimmer you can get really low values of voltage to the point where the bulb resembles an off state even though that it is powered on, and that is what this reading is for the most part here. But if we were to put the SD card back into the design and measure a load, it would continue to extend this file down further with the newer values. So that is the simple test.txt SD card file that is produced on the micro SD card. Thank you for watching. I've been Noah Bailey, and this was part 5 of my ECE5000 electrical engineering design project. We just took a look at the final product of my 120 volt AC load measurement device, which is capable of measuring voltages up to 250 volts RMS and up to currents of 20 amps, and it calculates the power and energy for these loads as well. In terms of a submission for this section, I made a 2-page brochure which includes specifications and other connection details, and further an in-depth look at the design, which will be submitted to the prof. The next portion of the project, part 6, is an in-depth demonstration and verification of my design, where I will go over multiple loads and multiple test scenarios and show extensively how the design works and show its true capabilities. But for now, thank you for watching. Once again, I've been Noah Bailey, and I hope you enjoyed.